Let's discuss the axial test. The strength of a material depends on its ability to sustain a load without excessive deformation or failure. This inherent strength must be determined experimentally. One of the most common experimental tests of a material is the axial test, in which an axial force, also known as a normal force, is applied to the material. The axial test can be either a tension test or compression test. From the results of the test, a multitude of important material properties can be gathered and quantified. To perform an axial test, a material specimen is made into a standard shape and size. Before testing, measurements are made of its initial length as well as its initial cross-sectional area A0. The testing machine applies an axial force to the specimen at a slow, constant rate until it fractures. The axial testing machine collects data of the axial force N and axial displacement delta in real time. From these data, normal stress and normal strain can be calculated as follows, then plotted on a graph of stress versus strain. And here is one of those stress-strain diagrams shown. Normal strain values are plotted on the horizontal axis, epsilon here, normal strain, and normal stress values are plotted on the vertical axis. So here we have sigma. Shown below is a typical stress-strain diagram for a ductile metal such as mild steel, which is an alloy of iron and carbon. So there's lots of information on this diagram. So first we have this region of elastic behavior, then this region of plastic behavior. In the elastic region of the test, the material can, quote, bounce back from a load. In other words, it can recover and go back to its original size and shape, so no permanent deformation. Then in the plastic region of the test, the material experiences permanent deformation. When it enters the plastic region, it is said to have yielded. The modulus of elasticity of a material, denoted by uppercase E, is a measure of its stiffness. So the greater the value of E, the stiffer the material. It is defined as stress divided by strain. It represents the slope of the initial linear region of the stress-strain curve. The modulus of elasticity, also known as Young's modulus or elastic modulus, has the same units as stress, since we have normal stress, which has units of Pascal, KSI, etc., divided by normal strain, which is a unitless value. The proportional limit, sigma sub PL, is the stress at which the stress-strain curve becomes nonlinear. The proportional limit often coincides closely with the yield stress. The yield stress, or yield strength you can call it, is the stress at which the material enters the plastic region of deformation, so entering the region of permanent deformation. Engineers often design structural members such that they do not enter the yielding or plastic phase of behavior, because in general we're trying to avoid permanent deformations. Strain hardening refers to the region after the yielding plateau and before the ultimate or maximum stress. And it's also important to mention that not all materials show a yielding plateau. Necking refers to the region after the ultimate stress. Here, in this region, during this time of the test, the specimen often develops a neck, which is a region of smaller cross-sectional area just before fracture. That would only happen for pretty ductile materials. Ultimate stress refers to the maximum stress experienced by the specimen during the test. And fracture stress refers to the stress at fracture when the specimen physically breaks.